In this video, we're going to discuss the properties or characteristics of all electromagnetic waves in general. First of all electromagnetic waves are transverse in nature. What that means is that the fields that make up those electromagnetic waves oscillate at 90 degrees, meaning perpendicularly to the direction of wave travel. So for example, if the wave is traveling, if the electromagnetic wave is traveling towards you, the electric field might oscillate up and down, which is at 90 degrees to the direction of wave travel. And the magnetic wave would oscillate at 90 degrees or left and right, which is again at 90 degrees or perpendicular to the direction of wave travel. So all electromagnetic waves, it doesn't matter which one, are transverse in nature. Secondly, all electromagnetic waves can travel through a vacuum. So because electromagnetic waves are comprised of an electric and magnetic field respectively, they don't require any particles to oscillate backwards and forwards or up and down, etc. Right? So because no particles are required, in this case we've got fields that are oscillating. So because fields can travel in a vacuum, therefore all electromagnetic waves can travel in a vacuum. A good example of this is visible light and infrared that's traveling, and of course ultraviolet as well, that's traveling from the sun to the earth. So we feel the infrared as heat radiation, we see the visible light with our eyes, and ultraviolet is good for our skin, right? So these are some electromagnetic waves that come from the sun. There are other cosmic radiations that come from space as well. So all of that later in the coming videos. Next, we've got the transfer of energy without moving any particles. Now, you think, hang on, why isn't there anything moving here? Because oscillation, inherently, the word oscillation means the movement of, right? So, how is it that nothing's moving in this case? Well, in this case, we're using the word movement in the sense that nothing is being relocated. So none of the particles are relocated from one position or one place to another. They're just oscillating, or the fields in this case are just oscillating backwards and forwards about a new position without relocating anything as a whole in general. Next, all electromagnetic waves travel at the same speed, which is the speed of light. In a vacuum that happens to be 3 × 10 to the power of 8 meters per second, which is approximately the same as the speed in air. So we sort of use them interchangeably. We do use 3 × 10 to the power of 8 meters per second when discussing the speed of light in air. Next, we've got the wave equation. So all waves, whether they're electromagnetic or not, obey the wave equation. So the speed of a wave, v, or velocity, is equal to the frequency, which is the number of cycles per second in hertz, times the wavelength, which is the distance between two successive similar points. So for example, the distance from one crest to another crest, or the distance between one trough to another trough, and so on. 2 successive similar points. So all waves, including electromagnetic waves, obey the wave equation. All electromagnetic waves do follow the basic wave behaviors as well. So all electromagnetic waves, including light, can reflect, meaning bounce off of surfaces, which happens whenever an electromagnetic wave, or any wave in general, encounters a boundary, right? So whenever an electromagnetic wave encounters a boundary, some of it or all of it is going to get reflected, unless it gets absorbed, of course. So all electromagnetic waves can reflect or refract, which means they can change their direction, so they can bend as they pass from one optical density or one medium to another. They can diffract, which is the spreading of a wave around corners, around edges. So all electromagnetic waves also diffract, or they can also get absorbed. Right? So there are different mediums, different substances where they might get absorbed. Whenever a wave including all electromagnetic waves, whenever a wave undergoes a certain wave behavior, so for example reflection or refraction and so on, the frequency never changes. Well, that's because the frequency depends on the source frequency. So the frequency of oscillation in the waves, in this case the electric field and the magnetic field, depends on the source that's disturbing, the disturbance that's creating those fields. Well, the movement, the frequency at which it oscillates basically depends on the source and not on the medium it's traveling through. The wavelength and the speed, on the other hand, do depend on the medium of travel. So while obeying the general wave equation, so for example, during refraction where the speed is going to change to cause that refraction, the wavelength changes accordingly. So if the speed decreases, the wavelength decreases accordingly, proportionately. And if the speed increases, the wavelength increases proportionately. Frequency always remains constant. And finally, none of the electromagnetic waves carry any charges, right? So I understand that there are a series of electric fields that are oscillating, but it's not a movement of charges backwards and forwards. It's just a field that's changing its magnitude.